And there they are.
Oh,
Started at the end.
starting at the right
So
time,
it's
yes.
very fast when they are two, yes.
So, welcome everyone. Thanks for coming and listening to us. My name is Lars Albertsson, as you heard. I've been spending the last few years as an independent consultant, helping companies building customized data platforms and extract value out of the data. And as of Monday, I'm transitioning into a startup, or formerly the brand, to build data platforms and extract value as a service for companies. But this is collaboration I did with Eric here from Bonnier News.
Yeah, I'm Eric, and I'm from Bonnier News. I'm a product owner and a programmer there. So, just a quick, if you don't know what Bonnier News is, we're a news organization in Sweden, one of the largest, and we have a bunch of magazines and papers. Just a taste of what we have. These are our two largest, which is the Expressen and Dagens Nyheter. Expressen is classic tabloid, and Dagens Nyheter is the morning newspaper. Right, so we're a company where we have a bunch of sub-companies that compete with each other, but our development department is like for all the magazines. And we're a data-driven organization, but we want to be more data-driven. And for that, we need to share data more. So we decided that we were going to build a common data platform for whole of Bonnier News. And we want to do this. One reason we want to do this is because we want to democratize the data in the whole in whole Bonnier News. And so we decided that we're going to create a small team and just do a little proof of concept. So we decided to do a scope. So we decided to just choose our 3 biggest brands with the most value impact. We also choose to scope out the data that we're going to put in this platform. So only the behavioral data, the technical data, so no content data. We also had to decide upfront which cloud we're going to use. We were transitioning off all Microsoft products, so we didn't even think about Azure. So our 2 competitors were AWS and Google Cloud Platform. We ended up choosing AWS because that was our pragmatic choice, right? Everyone knew how to use AWS, and also our DevOps team were building a new platform for all applications in Bonnier News, and they chose AWS to host that. We also, before we started, chose how we're going to develop this platform. And we come up with the idea of use case-driven development. So we're going to find use cases that produce value for a company and build the platform based on that, and not just take all the data we can find and put in like S3 and say, okay, we're done. And we're going to start with simple use cases that still produce some value for people. So finding a pain point for someone, getting data in that. And this is kind of the thing that we have worked with. So we find a small use case that provide value, evolve the platform based on the requirements, because the use case is gonna, okay, we need this and this and this data source. We get some new data into the platform, and then we iterate on top of that. So that's how we chose to build this data platform.
Splendid, thanks. So why does one build a data platform? In absence of a data platform, if you want to do data-driven innovation and combine data from various parts of the company, this is kind of what it looks like. If you have a service-oriented microservice architecture, the data lives in the different services and they're owned by different teams. So if you want to go out and combine various sources of data, you need to go out and speak to those teams. You need to get into their backlog at priority. The data needs to be of decent quality so that you can use it, preferably with some history from way back, and you need to figure out a way to extract it from their service. This amounts to a lot of friction. So what successful data-driven companies have done instead is to build a data platform. The enabling technology here was Hadoop, introduced some 10 years ago now. It made it economically feasible to throw all of the data that you have in the company into one big pool called the data lake. This became so popular that actually somebody figured out, hey, it would be great to do this as a real-time thing with streaming services as well. And then Kafka was the enabling technology. We do have a streaming part of the data platform built on not on Kafka, but on NATS and Spark streaming. I'm not going to speak about that and scope it out of the presentation. So we'll focus on the batch side of the platform and the data lake. Now, in many companies, this ends up being a fairly large, bombastic project with management support, lots of people involved and so forth. And it typically takes like between 6 to 24 months to get up and running and get value out of this platform. I've seen a handful of such scenarios. Now, we were in a news organization. Like, in news contexts, it either happens today or it's useless by definition. So we had a very different culture. So as Eric said, the approach we took was to be driven by use case. So we made up a sketch of this is what we want the platform to look like. And then we took the simplest use case we could find and built just enough to serve that use case. It was a fairly standard reporting use case, but it did deliver value in terms of automating things that had been done manually in the past. So we dug out we went to the teams that own the data that we wanted to have a source, dug out that data, made a refinement pipeline, and produced value in the end. Now, the first time you do this, there's the same friction as if you didn't have a data platform. But with time, as you onboard more data into the lake, the friction decreases, and you are enabled to innovate faster with data. So what does a data platform approximately look like? At the very end there, you have your traditional services. They store or produce data. Either they store data in databases. In that case, you dump the databases on a regular basis and put the information to the lake. They can produce events like page views and business events that happen in your system. You collect these events and put them into the lake in buckets or data sets of like 1 hour each or 1 day each. The raw events that you collect from the outside, you put in something called a cold store or sometimes the raw zone. Data put there is never changed. It's frozen. And that gives you some degrees of freedom. For example, you can go back and do things all over again if you get them wrong. You're not allowed to store personal data forever. So on the path in, if you're collecting data that relates to people, you split them out and separate the personal and non-personal data. From there, you do processing steps where you step-by-step refine the data. You clean it, aggregate it, and towards the right end, make more and more like application-specific things like build recommendation indexes and so forth. Each of these steps is called a job, and the intermediate results are called data sets. And this, when you put it together, is called a pipeline. It's not the same as a CI/CD pipeline. This is a data pipeline, but it has similar properties. So each of the data sets are immutable. We can rebuild everything from scratch if we want to. This thing is held together by something called workflow orchestration. That's kind of the data equivalent of Terraform. We use a tool called Luigi, which you see a snapshot here. It's similar to a build system tool, so it knows what things need to be built and what things have already been built and so forth. At the end here, some artifact of values produced, and these artifacts of values are either given to online services for if you do in recommendations or fraud or pushing data to users and so forth. Or they're used internally for like products insights, business insights, and so forth. Now, some of these fancy things are the things that you see in media, like AI stuff, but this is actually what tends to render most value for companies, getting better insights in what's going on. So what are the benefits of working in pipelines like this? So one is it makes things easy to change. So if you want to change something in your steps of processing, it's easy to build a parallel pipeline that takes the new kind of information and run these in parallel and compare the results and so forth. And when you switch over from the old one to the new one, you can keep the old one around and switch back if you need to. This enables you to move faster. It's also easy to be flexible here on the egress side, the last step where you spit things out of the lake to other storage you call egress. So in our case, we started with, in most cases, we had a Postgres database here for business insights, but some things didn't work on Postgres, so we also added a MySQL database. Not everything worked with MySQL, so we had to keep both of them around. This is very simple to do. And if we decide we need another one, it's easy to backfill from the old data in the pipeline. One of the scenarios we had was that there were people out here using things like BigQuery and Redshift for analytics purposes. And these tools are very powerful, but they can also be fairly expensive. For example, in BigQuery you pay per terabyte queried each time you do the query. So it turned out actually to be cost saving to do pre-aggregations and then serve aggregated data to the end users. So it is also a very forgiving environment in terms of screwing up. So if you have create a bug in your batch processing code, you will produce some bad data in the end. If this service is of importance to you, you will keep several versions of the data. So when you notice things are going bad, for example, the users are responding bad to or worse to your recommendations, you can switch back to an older version of the data, figure out what went wrong. When you fix the bug, you push the fix, and then you just remove the faulty data sets, and the workflow manager will automatically refill everything they have, or refill everything that was broken or missing. This gives a very quick time to repair if things go wrong. If the bug is simple, it would typically take half an hour or so to get up and running again. So since it's forgiving, it enables you to move faster. The previous two benefits are also, you get these two benefits also from streaming data pipelines. This one is specific to batch pipelines. So you've seen the business view, and now if you look at the deployment view, the technical view, if you have an on-premise installation, it typically looks something like this. The core is a Hadoop cluster here that is used both for storage and for computation. In the dawn of time, we were using MapReduce. Nowadays, you typically put Hadoop and Spark in one cluster and run Spark for computation. At the edge of the cluster, there are nodes called edge nodes, and those run the workflow management and the coordination of the jobs here in the cluster. And they are coordinated by a single server, which essentially serves as a mutual exclusion, preventing two jobs from running at the same time. You typically build an artifact per pipeline that contains all of the necessary code to run one of these pipelines. So Spark processing code, Luigi workflow definitions, and whatever config you need. You pack it up in some kind of standard artifact, and you schedule it, you install it, and then put a cron tab to sort of kick off the computation every once in a while. So it runs daily. It says daily here, and this is hourly. This is a sort of pattern of anti-fragility. So if things fail, we want to try them again later. And things frequently fail, so this method of retrying over and over again makes the system robust, even though individual components might fail. If you're in the cloud, looks similar. You typically have a managed Hadoop cluster. Most companies that are in the cloud no longer use the Hadoop cluster for storage, but uses some cloud object store as data lake storage. The artifact that you deploy is typically now Docker image and you put it into like Kubernetes and use this Kubernetes cron to schedule it. So fine, what we did was not like this. We removed the Hadoop cluster and instead ran all of the computation inside Kubernetes. We're still using Spark as a processing DSL because it gives a nice abstraction in terms of expressing data processing. But we're running it with what's called master local. All of the computation is running within one container. Now, this means that we cannot parallelize the computation outside one container, which means that we cannot scale to huge data sets. But we're Swedish newspapers, right? The amount of people in the world that speak Swedish are like 10 million. They are not able to generate all that much data so that we won't fit in one node. The largest nodes that you can get on Amazon have like 4 terabytes of memory and 128 CPUs. So all of the data that we'll have will safely fit into one node. We can still use thread level parallelization, even though we're in one container. We're in an Openshift environment, the platform that Eric mentioned. So this is what our CI/CD pipeline looks like. We have a monorepo. It's not a monorepository for the whole organization, but for the whole data platform, so all data processing lives there. We automatically build each pull request, and we have a mechanism for only running a subset of the tests pertaining to the pipeline being changed. Once we merge to master, there is a standard like Openshift pipeline that we use, which builds Docker images, put them into the registry, and from there we deploy them on Kubernetes. In addition to that, we're running a doc build on the side to build documentation, and we're running end-to-end tests, which test full pipelines or series of disconnected pipelines. These CI tests typically run one job in isolation. So the tests are written in Scala tests, whereas the end-to-end tests are written with the workflow, using the workflow manager. The CI tests there are designed to speed up developer experience. The end-to-end tests are designed to not to catch the business logic, but to catch integration problems in the pipeline. And they are designed to be as realistic as possible, so they run towards a separate test data lake. So this is visualization from Luigi, looking at the pipelines. Each pipeline is a pillar here. And I'm not sure, this is a very simple pipeline. It says DFP something here. It reads double-click for publishers data from Google and does a simple aggregation and spits it out into a Postgres egress database. Each of these pillars is probably like 1 hour of data. The blue things here are jobs running at the same time. So we do exploit parallelism in the workflow management, but we do not exploit parallelism within each of these jobs. This is a simple pipeline. This is a complex pipeline. And this is implementation of some of the GDPR requirements related to splitting out private data and also creating registry extracts from as required by GDPR. You're allowed to ask us and say, what data have you got on me? And this is the pipeline that spits that out. So this is an excerpt from some of our OpenShift monitoring. In this graph here, you can see that on a daily cadence, we run a whole bunch of intensive jobs, at most 5 at the time of the current situation. This is the number of pods that are created. You can see some of them climb up here, which indicates that we are asking for parallelism in Kubernetes. So for one job, we can schedule many parallel pods, which then makes the cluster auto-scale and allocate a bunch of more nodes, so we say a daily cadence here as well. We're using spot nodes. Since these are batch jobs, they are like, in theory, atomic, and the data sets are immutable. We can survive that nodes get killed, so we save like 80% of the cost by using spot nodes all the time.
Yes, GDPR. Lars mentioned it before. I imagine everyone here has had to deal with the GDPR. We started development before it went into force, but we always had it in back of our mind. And two things that we really need to think about are the Article 17, the data retention and data deletion. So we can't just keep data forever anymore, and you should never have had that. And when a user says, hey, I don't want you to have my data anymore, we need to delete that. And so we implemented this in the data platform. So when we have a data set which contains personal data, with that data set comes a JSON schema file that identifies what we can key on and also what fields are personal identifiable data. With that ID, we create a encryption key, which we then encrypt that data with. And then that encrypted data is stored into the lake. So for the retention part, each JSON schema also says how long we're allowed to keep this data. So each data set has a retention time. We continuously create new keys each 30 days, each month. And when that retention time, we meet that retention time, we just destroy the key and we can't decrypt the data. And for the right to be forgotten, the deletion request, we do basically the same. So we get a list of users each day who has said, I don't want you to keep my data. We find the keys for those users and then we throw away those keys. And this is the approach that both, I think, Spotify and Google has also taken. So some of the use cases that we are currently having in production. So we have a machine learning system, and a data lake is great for like leveraging and building machine learning system on top of. And that system just tries to predict, are you gonna see the whole video in the app? And if you think you're gonna watch the whole video, we're gonna show you an ad. And we also create a bunch of reports for people. So we do daily reporting to the ads team about like, okay, how many people watch this ad, etc. But we also do weekly reports for that for the site teams, and they do A/B testing on that data. So they can decide if the changes we have done to the site has also changed how people interact with the ads. And of course, GDPR registry extract is a great use case for the lake. Since we have all the data, we can just merge that data and send that data back to the users to be viewed. So some of the lessons learned.
Summary slide?
No, I changed us. Cloud selection is influenced by data location. Most of our data is in Google Cloud Storage. So we incur an extra cost when we try to get that data from Google. And since we are, cost is one of our constraints, that was something that we would have liked to know in the beginning. And Lars, the Kubernetes thing?
Yes, so one of the reasons we ended up with this Openshift solution was that we are then operating in the same operational platforms as many of the online teams. So there was a harmony there, and we had great support from the team building that platform. And without that support, we would have been significantly slower. So the harmony there worked great. No Spark cluster. I have spent way too much time in my career debugging Hadoop and Spark clusters and the problems related to cluster computation, not only keeping the clusters alive, but debugging things, serialization problems, data skew problems, and so forth. We have none of that. It's much more convenient, and we waste much less time on that. And we did get the autoscaling to work well after a while. We noticed that the interaction between OpenShift and AWS for autoscaling is geared towards long-running services and not batch jobs, which we are running. So there was a bit of tweaking, but it worked sufficiently well. Some other lessons learned that I forgot to put up is the cultural challenge in having multiple competing newspapers on one platform was interesting. So some of the teams were not as enthusiastic about sharing their data as you might have hoped for. We addressed that by early starting with like a data governance sort of structure, which basically defined the rules for playing in the data lake, and that helped a bit with coming over those issues.
So in summary, the use case driven approach worked very well. Our first pipeline took 3 weeks, and Lars told us that it usually takes months to maybe a year to get the first pipeline to production. We managed with a small team. We're now 4 people. We've been 2.5 usually. Like, keep it simple, keep the use cases simple, and try to find small use cases to drive value, and that will work very well. And right now we have 10 to 15 pipelines that are in production, producing good data for different teams across the whole organization. I think we're done with that.
Yeah, we've been running this since January, so this is like 9 months in since we started from scratch, basically.
And since I speak quickly when I'm nervous, I think we have some time for questions.
Can we?
We have a bunch of questions.
So I assume the streaming side is triggered by data coming in through the system, and that triggers a job to begin executing. But are the batches, are they triggered by data coming in, or are they pulled by like some kind of timer, like once a day we have to pull this data through the pipeline?
So it depends. If you back further to the pipelines, further. So here, there are different forms of data collection. Data collection is the process of getting things from here to here, basically. Event collection here, that is a push flow. So events come in here, and in a large-scale environment, these events are typically go over Kafka or something similar, and then you have a mechanism that buckets them on an hourly basis so that they become data sets. And then when the hour has come to an end, you freeze that data set, and it's immutable thereafter and no longer touched. Once an event data set is in place, the workflow management says, oh, I now have a new data set, so I can run the pipeline. For dumping things, that's a pull mechanism. So you typically go out to the database and initiate a dump. And if it's a small database, then you're just doing a SQL query. If it's a large database, this cluster here can effectively DDoS the database. So you have to be a bit more careful. There are tricks for that. We also have cases where we go out to an external API and scrape. And that's also a pull thing. And the pull things are driven by the workflow management.
That's exactly what I wanted to know.
Hi. Thanks for the great talk. What's your experience with spot node availability in Amazon? Like, have you had issues where Amazon is telling you, sorry guys, no compute for you?
We haven't run it that long, so we haven't.
We just switched to spot nodes.
Yeah, like two days ago.
Yeah, a couple of years ago, I was at the competing newspaper in Sweden, news conglomerate in Sweden called Schibsted, and we were running in Amazon using spot nodes as well. But this was a number of years ago, so the dynamics are like different. I know there were people, some other team there hacking like dynamic bids and so forth in order to get this to work, and that was quite painful. I didn't have any personal hands-on experience with it, so sorry.
So if I understood you correctly, you are addressing GDPR by basically encrypting your data and throwing out the keys once you don't need it anymore. Aren't you afraid that after a couple of years there will be new algorithms, innovations, and most of your data will be easily decrypted?
Yeah, that's an FAQ. Okay, if I take it.
Sure.
So I hear that a bit. I was in a heated Twitter argument recently on that topic. As Eric said, this is like industry standard. Spotify and Google also rely on these things, and they've publicly announced this. The risks are an encryption algorithm is found to be flawed, and someone can break into it, right? That happened with the RC2 algorithm, for example. If that is the case, we have the data locked up, right? It's not published anywhere. So we have the data locked up, so we can work a bit and go and discard it. And also if like Blowfish or some common algorithm is fundamentally broken so that it's easy to encrypt it, there are, the whole world will burn, and it's not likely that anyone would care that if somebody breaks into S3, they might see what newspaper articles you read like 2 years ago. So it's a matter of weighing things. Second, the long key encryption algorithms cannot be brute forced. There's just, if you can do an energy reasoning and say if you're brute force attacking an algorithm, it requires at least the movement of one electron, and if you have 2K or 4K or whatever the limit is, you require more energy than the sun contains. So there has to be a flaw in order for it to be broken, or there has to be some quantum mechanism that we don't know of today. But the GDPR is a law, and it's not strict. There's nothing in the laws that say you must do exactly this. All the laws are soft, and there are reasonings about what the risks of privacy leaks versus the efforts required to protect more privacy. So it's a soft weighing of things. I hope that answers the question.
I have an additional question. Most auditors think that this is compliant to GDPR.
The lawyers that I've spoken to think that this is compliant, yes. And there are similar reasonings about backups. You have private data on backups way back. Most lawyers say that, no, you don't have to go and rewrite all of your backups. It's so small risk that leaks. But you have to clean them if you restore from the backups. But I'm not a lawyer, right? So don't sue me.
Well, thank you to Lars and Eric.